This might be the last video of the semester because these sections are really short and very easy. We're going to be using the calculator again to do the work, just need to explain some concepts. But as long as my computer doesn't stop recording video while I'm going through the lecture, we should be able to knock this out in probably like half hour. So, 12.3 is the regression equation. So in the previous section, we went over scatter plots, and I showed you how to make a scatter plot with the calculator. Now, from this scatter plot, what we can do is make something called the least squares regression line. So the least squares regression line is now y bar is equal to b x bar plus a. So this is the line, this is the equation of the line of the best fit for n data points x comma y. So remember what we do, we go around, we collect bivariate data, height versus weight, something like that. And we plot all these data points and we get a scatter plot. Now from that scatter plot, what we can do is find the equation of the line that best fits the data. Now we're going to go through what it means to be best fit, what least squares means. So let me draw you just some random scatter plot. And if I look at the data, it looks like it has a positive correlation, right? And they're all like tightly packed between right here and right here. If I were to draw a line pretty much through the center as best I can of these dots, maybe it looks something like that. Now, let me get a different color. Let me get red. What we do is we do this for every single data point. I'm only going to draw it for one. This data point right here, this distance right there. So 1 point, this point right here, this one is our y sub I. The coordinate, the y coordinate of our ith point, whatever point we're talking about. And then this blue one right here, we're just going to call y hat. We're going to call it y hat. That is the predicted value of this equation. Now, what we do is we make something called a residual. What a residual is the actual value, so we call it epsilon. This is Greek letter epsilon, little epsilon. The ith residual is equal to, you take the actual value and you minus the predicted value. That's all you do. Actual minus predicted. Now, sometimes these epsilons are going to be positive, sometimes they're going to be negative. Here, epsilon will be negative because my actual value is smaller than my predicted value. If my actual value is smaller than my predicted value, this is going to be a negative number. So these little residuals are distances, and what we want to do is we want to add up all these distances. However, we don't want negative distances because that's going to cancel out some of our positive distances. So sum of square errors, SSE, sum of squares error, is equal to the sum of, you take every single one of these residuals, you square them, and then that's what the sum means. You add them all up. Now, we're not actually going to be doing this, okay? This is just explaining to you what's going on. So this is equal to the sum of y sub I minus y hat all squared. So you just find each individual residual, you square it, and you add them all up. Now, this is going to give us a function, okay? What we want to do is we want to minimize these residuals. So you need calculus to do this, okay? So that's why we're not actually going to go through and do this process. But using calculus, the idea is that what it does, this creates a function that we can measure, and it tilts this line and positions it somewhere through here. And using calculus, we could find it where all these distances is a minimum, meaning that this line is as close to every point as possible as it can be, okay? Any other way, if you calculate these distances and add them all up, it's going to be a bigger number. It's going to be further away from every point as it can truly be. It can be a lot closer. So that's what, if you look at the term, least squares regression line. So using calculus, we find the minimum of this. That's what it means by the least squares, because we're squaring everything. Regression means we're using our residuals, so the least squares of the residuals. Okay, that's where the name's coming from. So that's just explanation of what we're doing. Now, the resulting equation is this. Y hat is equal to bx hat plus a. I mean, we don't, sorry, I kept saying hat, I meant bar. We don't really need the y bar and x bar there. We could just say y equals mx plus b, or bx plus a, sorry. Now, a is usually found by finding all the averages of the y's minusing b times the averages of all the x's. So we could find that, Now, here's the equation of b. Now, it's a really horrible equation. I would not recommend doing this by hand. Oops, it's a really bad sum sign. There we go. So what this is saying is you find the average of the x's, you find the average of the y's, you take each x value in your data set, you subtract it by the mean, you take each y in your data set, I don't have it written here, but these actually should have like subscripts down there. So the ith data point, so the first data point, second data point, third data point, so on, so on, so on. And you just keep subtracting the means, and then you get those numbers, you multiply them, you add them all up. Now on the bottom here, you do the same calculation here, but you square it and add them all up. You cannot cancel this and cancel that, so don't do that. That'd be incorrect, so don't do that. So again, we don't actually have to do these formulas. The calculator is going to do this work for us. It's going to find us our B and find us our A. So we're going to use these examples. I would recommend putting this first example in your calculator into list 1 and into list 2. And then the second example, Now, if you read it, there's a typo. I think they miscounted or mistyped when they were doing this. It says the data below are the final exam scores of 10 randomly selected statistics students. If you look at the data set below, it only gives 6 data points. So I think that's, they meant to say 6 randomly selected statistics students. So again, that's just a typo. I just copied that problem right out of your book. So put that list into list 3 and list 4. We are going to use both of these examples in the next section. Okay? So you can pause the video and enter them into your lists. I'm going to show you how to get the least squares regression line. Now, edit. As you can see in my list 1 and list 2, ignore list 3 over here. List 1 and list 2, I have the third exam score and the final exam score right here for the first example. And then if I scroll over, list 3 and list 4, I have the second example about the statistics students. Okay, I've got the 6 hours studied here and their score over there. So again, pause the video, get these entered, make sure you look over them, make sure you entered all the numbers in correctly, and then when you're ready to do that, resume the video and we can go on. So what we're going to do is use something called the linear regression t-test. Okay, I guess T is also capitalized. So linear regression t-test. Now this is a t-test because you got a sample of points. Anytime you have a sample of points, you do not know the population standard deviation. You are using the sample standard deviation. So that's why we're doing a t-test and we cannot do a z-test here. So when you go to that menu, or how to go to that menu, you hit Stat, go over to Tests. The same spot you found your z-tests, your t-tests, your z-interval, your t-interval, your one proportion z-test, and one proportion z-interval. Okay, you've been here before. So it starts over at Edit, you go over to Test. It's easier to scroll up, and there we go, Linear Regression t-test. You hit Enter, and it brings up a menu. Now, we're going to do the first example right now. It says a random sample of 11 statistics students, I guess they're both about statistics students, produce the following data where X is the third exam score out of 80 and Y is the final exam score out of 200. Using the scatter plot, does it appear that we can predict the final exam score of a randomly selected student if we know their third exam score? So they want to know, can we use our least squares regression line to predict someone's final exam score? And that's going to be the question in section 12.4. Can we actually use this line? So, since we entered in the third exam score into list 1, your X list is list 1, your Y list is list 2. Frequency, you're always going to make it a 1. And then I could just tell you now, the third option where it says right here, it says beta and that's a row, beta and row. What we want to choose is the not equal to. Okay, this is going to be for the hypothesis testing, which I will discuss in the next section. And then regression equation right here, what we want to do is store our equation into our y equals. So for you, it's probably blank right now. So what you want to do is you want to hit vars. It's right here, right where you used to go for distribution, but don't hit second. Just hit vars. You're going to go over to y vars. So you got to click right. You hit enter. And, oh, you hit enter on function and you go to y1. There you go. And now you should go to calculate. So, I guess I'd show you what I got real quick. That's what I got. You could scroll down. It'll tell you your A, B, S, R squared, and R. We're going to go through what these things mean. All right, so first off, at the very top, it says y is equal to a plus bx. And then if we scroll down a little further, it tells us what the A is. It's negative 173.51. B is equal to 4.827. Now, if you scroll down, you see S is equal to 16.142. R squared is 0.4396. And we have another number, R is equal to 0.663. Actually, let's see. We have some other numbers at the top. We've got a T number, a P number, and a DF number, okay, degrees of freedom. We'll talk about those in the next section. These are the numbers I want to talk about right now. So, this tells us what our A is, this tells us what our B is. So if we wanted to, we could graph the equation of the line. Right here is the standard deviation of our sample, calculated it for us. This right here is the correlation coefficient, okay? We'll talk about that in a bit. And this, coefficient of variation, okay? We're not going to need this number right here. All right, so remember how we stored the equation into our calculator? Let's go ahead and look at that equation. If we go to y equals, there's the equation. It's stored into our calculator. We don't have to do it because we told it to store it into there. And not only that, hit second y equals, go to plot, turn it on. Now make sure it's list 1, list 2. I showed you a way of turning it on and off really easily. You see how it's darkened up here. It says plot 1. I can go up there and hit enter, and it'll turn it off. Okay, so right now it's off. So if I go up there and hit enter, now it's on. So we already had scatter plots stored as what kind of graph we wanted to do. And if we hit zoom, we hit number 9, it'll draw the scatter plot and the linear regression equation for us. So as you can see, it kind of looks like it's a good fit. There's a lot of points scattered near the line. There are some points scattered off the line, but this is the line that best fits the data. It's as close to every point as it can be at one time. Okay? So let's go ahead and do it for the next example. Now, I already told you put these into this next example into list 3 and list 4. Leave them there. Again, we're going to use these for the next section. So I'm hitting stat, going over to tests, scrolling up to linear regression t-test, hit enter. Now hit second L3 for list 3, second L4 for list 4, not equals to regression equation. Since we already did it, it already has y1 in there for us. And now all I have to do is go to calculate. Okay, so let me write these numbers up here. A is 67.349. B is 1.066. S is 13.77. R is 0.0502. And R is equal to 0.224. All right, so, and if you want to get R squared, you know R, you literally just square this thing and you get this, okay? So they give you two values. We're only going to need this one. So this is the information that we have for the second example. The data shows the final exam scores of 10 randomly selected statistics students and the hours they studied for the exam. Okay, so let's see. Let's go ahead and make a graph of it again. So second y equals this time. Remember, our plot 1, x list and y list, was in list 1 and list 2. So we got to go down and change that now to list 3 and list 4. Oh, so now I hit zoom, I hit 9. Now, as you can see, the linear regression line does go through the middle of the data. However, all the points are scattered way far away from it. So in the first example, it seemed like the linear equation did work well with the data. You probably could use it for predictions. This one, not so much. Okay, you probably wouldn't rely on this one for predictions. So now let's talk about what this R means here. What is the correlation of coefficient? Now it has a really awful formula. You can look at my notes. I'm not gonna write it. It is really bad, but we're not gonna calculate it by hand. I only have that in my notes so you guys could just see what it looks like. And we're going to use the calculator to get it. We already did use the calculator to get that R value. Now, there are some properties of R. Now, R is always between, so negative 1, R is less than or equal to 1. R is always between negative 1 and 1. Okay? So, positive R, all this means is that the slope is positive. There's a positive correlation. If I were to draw the linear regression equation, it's going to look something like that. It has a positive slope, meaning that there's a positive trend in the data. As the independent variable goes up, the dependent variable also goes up. Now, R is equal to 1 is a perfect fit. Perfect fit, meaning all the points land on the same line. Now you could reverse this. Negative R, slope is negative. So that means it has a negative trend to it, and R is equal to negative 1 just means every single point lies on a perfect line, okay? That means there's a perfect correlation, perfect correlation, perfect correlation, perfect positive correlation, perfect negative correlation. Now these also, R also tells us the strength of the correlation. So R closer to plus or minus 1, it doesn't matter, plus or minus 1, the positive and negative just tells us the direction of the correlation. Closer to plus or minus 1, the stronger the correlation. The closer R closer to 0, the weaker the correlation. And then R equals 0, no correlation. So those are just the properties of R. And what we're going to do is ask ourselves what value of R constitutes a strong correlation and what value of R constitutes a weak correlation. So that's what we're about to talk about in the next section for hypothesis testing. Alright, so this is section 12.4. And it's testing the significance of the correlation coefficient. Testing the correlation coefficient, the significance of it. So these have all the same elements of a hypothesis test that we had from Chapter 9. First, let me introduce you some notation. So this is the population correlation coefficient. Greek letter rho, little rho. That's how I write mine. If you see my notes, that's how Word writes theirs. I put a little tail on mine so it doesn't look like a P. Because if I did that, it'd look like a P. That's why I put the little tail. So like a backwards Q. So that's how I write it. That's a rho. And then this is the sample correlation coefficient. It's R. Remember, population parameters have Greek letters. Sample parameters have normal alphabet letters. Okay? So, let's see. R tells us the strength and direction of the linear relationship between our independent and dependent variables. Okay? We want to know how strong of a relationship, or how close to plus or minus 1 does this need to be for us to be able to use the regression equation to predict values? That's the question we're asking. The regression equation that we got from our calculator, can we use it to predict values? We're going to look at our R value to determine that. Okay? So we're going to do a hypothesis test. The null hypothesis says that there is no relationship. The population parameter correlation coefficient is equal to 0, meaning if you were to, and I just saw the video freeze, so I'm going to pause it here and we're going to do